What if you woke up tomorrow and learned a 10-kilometer asteroid would hit Earth in exactly 24 hours? Not a Hollywood movie plot, a genuine astronomical emergency with no time for a heroic space mission. Just one planetary revolution before impact. In the next 15 minutes, I'll walk you through the terrifying timeline of this extinction-level event, from detection to impact to the aftermath. Scientists estimate this asteroid would unleash energy equivalent to 100 million megatons of TNT, surpassing all nuclear weapons combined. Unlike dinosaurs, we'll see our approaching doom, the dawning reality of humanity's final day on Earth as the cosmic hammer approaches, the moment of discovery. Could we actually miss seeing a 10-kilometer asteroid until just before impact? Unfortunately, the answer is yes. Our current detection systems have significant blind spots that could allow even a massive planet killer to approach unnoticed until the final day. Modern asteroid detection functions like a global security network with inevitable gaps in coverage. This network primarily consists of automated telescope systems that methodically scan the night sky. Programs like NASA's Near-Earth Object Observations program use ground-based telescopes that take sequential images of the same patch of sky, identifying asteroids by their movement against the fixed background of stars. Once identified, these objects are tracked over multiple nights to calculate their orbits and determine potential Earth intersections. Space-based telescopes like NASA's NEOWISE complement this system by detecting asteroids through their heat signatures rather than reflected sunlight, allowing for identification of darker objects. Despite this sophisticated surveillance system, critical vulnerabilities remain. Ground-based telescopes operate only during night hours and clear weather, while space telescopes have limited coverage areas. The most dangerous weakness in our planetary defense is the solar blind spot, a cone-shaped region extending from the sun toward Earth, where telescopes cannot safely look without damaging their sensitive equipment. An asteroid approaching from this direction remains effectively invisible until emerging from this blind zone, potentially giving us minimal warning. The thought that a civilization-ending object could be rushing towards completely undetected is profoundly unsettling. Our hypothetical 10-kilometer asteroid approaching from the sunward side presents exactly this nightmare scenario. Despite its enormous size, it would remain hidden in the sun's glare until emerging from the blind spot less than 24 hours before impact. The first observation would likely come from a survey telescope during routine scanning, capturing an unusually bright object absent from previous scans of that region. The gap between theoretical detection capabilities and practical reality is substantial. While NASA has identified approximately 95% of near-Earth objects than 1 kilometer, thousands of smaller asteroids remain undiscovered. Even more concerning, new objects enter near-Earth space regularly as their orbits change through gravitational interactions or collisions. A 10-kilometer object would certainly be on our tracking lists if it were a regular visitor to our neighborhood, but a long-period object making its first close approach would remain unknown until visual detection. When the first images of our hypothetical planet killer appear on astronomers' monitors, it would trigger an immediate verification protocol. The detecting observatory would calculate the object's apparent speed and direction, recognizing characteristics of a very close and fast-approaching asteroid. This preliminary data would be immediately submitted to the Minor Planet Center at the Smithsonian Astrophysical Observatory, the global clearinghouse for asteroid observations. Within minutes, an automated alert would reach observatories worldwide, requesting urgent follow-up observations. The confirmation process would unfold rapidly as telescopes across different longitudes focus on the provided coordinates. Each additional observation would refine the orbital calculations, gradually building a more precise prediction. The growing dataset would reveal the trajectory intersects directly with Earth. Calculating the precise impact location with only hours remaining presents significant challenges. The initial margin of error might span hundreds or thousands of kilometers. As more telescopes contribute data, the impact ellipse, the region of possible impact locations, would gradually shrink, but complete precision would remain elusive until the final hours. Once the impact probability crosses certain thresholds, international protocols would activate automatically. NASA's Planetary Defense Coordination Office would alert the U.S. government through established channels. Simultaneously, the International Asteroid Warning Network would distribute the alert to space agencies and governments worldwide. Major space programs would receive data packages containing orbital parameters and impact assessments. Within the first hours after detection, emergency management agencies would activate under catastrophic event protocols. The United Nations Office for Outer Space Affairs would facilitate international coordination while national security councils convene emergency sessions. The information would initially be contained to prevent panic, but this containment would likely fail as astronomers independently confirm the approaching object. Our current detection capabilities could identify a 10-kilometer asteroid with 24 hours remaining. Our systems scan the visible sky multiple times nightly, and an object this large would appear dramatically brighter than typical asteroids as it approached. However, if it approached from the solar blind spot or during limited observatory coverage due to weather, detection might come even later. While detection would be likely within this time frame, certainty is impossible to guarantee. Our planetary defense system has significant gaps, which is why space agencies continue pushing for expanded detection capabilities, including missions designed to observe the sunward direction from strategic vantage points. What makes this scenario particularly frightening is that 24 hours represents the outer limit of plausible late detection for an object this size. A sunward approaching asteroid might be discovered with just enough time to confirm our fate, but too little time to alter it. As confirmation completes and impact becomes certain, the countdown begins on humanity's final day. Emergency broadcasts would reach government officials worldwide, while military communications networks carry encoded flash messages to command centers. In observatories across the planet, astronomers would track the approaching object with professional determination and personal dread, calculating the impact parameters as the data improves. What exactly would those final 24 hours look like for a civilization about to experience an extinction-level impact? How would governments respond? What could ordinary people do with their remaining time? As the countdown begins, the true scale of our vulnerability becomes apparent. The final 24 hours. 24 hours before impact, the first official notifications would reach government command centers worldwide. Emergency management agencies would activate their highest level protocols, initially containing information to prevent immediate panic. In the White House Situation Room, Pentagon War Rooms, and equivalent facilities around the globe, senior leadership would confront an unprecedented crisis with no viable solution. National security councils would convene immediately. Their standard protocols designed for earthquakes, hurricanes, even nuclear war would prove inadequate against a cosmic impact. Military leaders would quickly determine that nuclear interventions would fail. The asteroid approaches too rapidly for any existing technology to alter its course. The focus shifts to managing aftermath, like preparing for a hurricane that will engulf an entire continent. Tick. 23 hours remain. As astronomers refine calculations, emergency planners map destruction zones extending outward from the projected impact site, the vaporization zone, the shockwave radius, the firestorm perimeter, tsunami, vulnerable coastlines. The impact location becomes the terrible epicenter of a countdown clock pulsing across every emergency operations center worldwide. The harsh reality crystallizes: evacuation is physically impossible. Even with 24 hours of warning, moving masses of people fails at scale. Evacuation speeds during managed emergencies reach only 25-30 kilometers per hour under ideal conditions. This maximum collapses when millions flee simultaneously. During Hurricane Rita, evacuation traffic slowed to less than 1 kilometer per hour. Some traveled 12 hours to cover distances normally requiring 30 minutes. Tick. 20 hours remain. Simple mathematics reveals the futility. With destruction extending hundreds of kilometers from impact, even people traveling at a consistent 80 kilometers per hour, and possibly optimistic, could reach only about 1,900 kilometers in 24 hours. This assumes continuous driving, no congestion, unlimited fuel, and perfect vehicle performance. The realistic evacuation radius would be substantially smaller, perhaps 500 kilometers for most people. Transportation infrastructure fails under the strain. Highways become parking lots. Fuel supplies deplete within hours. Air travel capacity represents a tiny fraction of the affected population. Emergency services freeze in gridlock, unable to navigate congested routes. For most people within thousands of kilometers of impact, reaching safety becomes mathematically impossible. Tick. 18 hours remain. World leaders face an excruciating decision whether to inform the public. This represents a profound ethical dilemma. Transparency allows personal choices about final hours, but triggers widespread panic. Withholding information preserves order, but denies people agency during humanity's final day. Different nations make different choices. In our interconnected digital age, astronomical observations spread rapidly. Amateur astronomers detect the object independently. Information leaks through unofficial channels, racing across social media faster than government communications can respond. Tick. 15 hours remain. Communications networks strain beyond capacity. Cell towers overload. Internet bandwidth saturates with video streaming, downloads, and desperate communication attempts. Emergency communication systems collapse under demand, further complicating coordination efforts. Information spread varies by region and technology access. Urban populations with high smartphone penetration receive news almost immediately. Rural communities with limited connectivity might remain unaware for crucial hours. This information inequality creates drastically different responses across geographical and socioeconomic lines. Tick. 12 hours remain. Misinformation proliferates alongside accurate reports. False claims about safe zones, government bunkers, or rescue plans spread rapidly. Social media algorithms amplify emotional content rather than factual information, distorting public understanding. The psychological impact follows patterns seen in previous disasters, but at unprecedented scale. Some enter denial, continuing normal routines despite evidence. Others experience paralyzing anxiety. Many turn to religious frameworks to process the impending catastrophe. The countdown heartbeat grows louder in everyone's mind. Tick. 8 hours remain. Cultural responses vary based on existing social structures. Regions with recent disaster experiences activate community support systems more effectively. Societies with strong central authority maintain order longer. Countries with ingrained disaster preparation cultures respond more methodically initially. For emergency officials, the situation creates profound professional conflicts. Trained to manage crises, they face a disaster beyond mitigation. Military forces deployed to maintain order rather than evacuate, with personnel torn between duty and family. Tick. 4 hours remain. Religious institutions become focal points for communities. Attendance at services reaches unprecedented levels. Improvised ceremonies emerge in public spaces. Digital platforms host virtual vigils connecting people across distances. These gatherings provide psychological comfort but create concentrated groups that complicate emergency management. Economic systems cease functioning in informed regions. Financial markets collapse. Banking systems overwhelm with withdrawal attempts before shutting down. Commerce shifts to direct bartering for immediate needs. Tick. 1 hour remains. How likely is this scenario? Impacts from objects 10 kilometers or larger occur on timescales of roughly 100 million years. The last known impact of this magnitude occurred 66 million years ago, eliminating approximately 75% of species, including non-avian dinosaurs. The probability during any human lifetime is extremely low, approximately a 0.01% chance. Astronomical observatories provide increasingly precise tracking data. The asteroid becomes visible to naked eye in final hours, a new star growing steadily brighter. Its apparent size increases dramatically in final minutes, transforming from bright point to visible disk. For those on the daylight side of Earth, the approaching object might remain invisible until atmospheric entry, when the countdown reaches zero and physics begins its unstoppable sequence of devastation. The moment of impact. In the asteroid's final moments approaching Earth, its velocity reaches approximately 20 kilometers per second, nearly 60 times the speed of sound. At this stage, it transitions from an astronomical object to a physical projectile on a collision course with our planet. Any observers with telescopes trained on the correct patch of sky would witness the asteroid growing rapidly brighter, transforming from a faint dot to a brilliant star-like point, visible even in daylight. For those directly beneath the approach path, the asteroid would remain invisible until it enters Earth's atmosphere. At roughly 100 kilometers above the surface, the massive object begins interacting with our atmosphere, compressing air molecules in front of it with such force that they ionize, creating a brilliant flash expanding across the sky. This celestial wrecking ball announces its arrival with an unnaturally bright light growing dramatically in intensity over mere seconds, visible hundreds of kilometers away. Unlike smaller meteoroids that burn up in our atmosphere, a 10-kilometer asteroid powers through the atmospheric shield surrounding our planet. The thin layer of gas offers negligible resistance to an object of this mass. The asteroid punches through the atmosphere in less than 5 seconds, maintaining nearly all of its cosmic velocity as it reaches the surface. Commercial airliners typically fly at about 10 kilometers altitude. The asteroid crosses this entire distance in a half second. The moment of contact between asteroid and Earth unleashes one of the most energetic events in our solar system. With a mass of approximately 10 trillion tons and velocity of 20 kilometers per second, the object carries kinetic energy equivalent to over 100 million megatons of TNT, more than 6,500 times the entire nuclear arsenal at the height of the Cold War. This concentrated power releases more energy than human civilization has produced throughout its entire history in a single moment. Upon impact, the asteroid's leading edge decelerates violently. The extreme pressure creates temperatures exceeding 30,000 degrees Celsius, 5 times hotter than the sun's surface. Both the asteroid material and Earth's crust vaporize instantly, converting from solid to gas. The asteroid, though primarily solid rock or metal, behaves like a fluid under these conditions, deforming and flowing outward from the impact point. Simultaneously, a powerful shockwave propagates through Earth's crust at approximately 5 to 8 kilometers per second. This compression wave momentarily transforms solid rock into a liquid-like state, causing the surface to depress before rebounding in a massive upheaval. Within seconds, the crater formation begins through excavation and compression. The initial contact vaporizes material at ground zero while driving crustal material downward and outward. This process creates a transient cavity, potentially extending 30 to 40 kilometers deep, possibly reaching Earth's upper mantle, with a width of approximately 100 kilometers. This unstable configuration quickly begins its transformation as gravitational forces cause the central peak to rebound upward while the surrounding rim collapses inward. After several minutes of adjustment, the crater stabilizes into its final form, spanning approximately 150 to 200 kilometers, roughly the distance from New York City to Washington, D.C. As the crater forms, an extraordinary ejecta blanket blasts outward. This material, vaporized rock, molten debris, and solid fragments, shoots away from the impact in expanding curtains. Some ejecta launches nearly vertically at speeds exceeding escape velocity, reaching hundreds of kilometers altitude before much returns to Earth hours later. Other material expands laterally in a supersonic curtain of debris. A blinding fireball emerges from the impact point within the first second. This blazing sphere, reaching temperatures similar to the sun's interior, expands rapidly as it rises from the crater. The fireball emits intense thermal radiation across the electromagnetic spectrum that travels outward at light speed. This thermal pulse ignites combustible materials hundreds of kilometers away, starting widespread fires well before the pressure wave arrives. Unlike nuclear explosions that form mushroom clouds, extending 20 to 40 kilometers high, this impact fireball punches completely through Earth's atmosphere, potentially reaching hundreds of kilometers in height before dissipating in near-Earth space. The displacement of air creates a supersonic pressure wave, expanding in all directions. This shockwave initially moves at many times the speed of sound, with overpressure exceeding hundreds of pounds per square inch near the impact, enough to demolish reinforced concrete and instantly kill any living organisms. This atmospheric assault weakens with distance, but remains destructive for hundreds of kilometers. After the initial shockwave passes, hurricane-force winds rush back toward ground zero to fill the partial vacuum created by the explosion. The energy released in this impact dwarfs our most destructive weapons by orders of magnitude, comparable to the force required to briefly stop Earth's rotation. The destruction radiates outward at different rates: thermal radiation at light speed, atmospheric pressure waves at several times sound speed, and seismic waves through the crust at 5 to 8 kilometers per second. This creates a sequence of devastation unfolding over minutes following impact, with each mechanism carrying death further from ground zero. The shockwave of destruction. The initial blast wave radiating from the asteroid impact transforms into the primary killing mechanism beyond the immediate vicinity of ground zero. This pressure wave moves through air as a supersonic compression front, traveling at several times the speed of sound in the first minutes after impact. Unlike a typical explosion where pressure decreases predictably with distance, an asteroid impact generates a complex multi-layered shockwave whose behavior more closely resembles that of nuclear weapons, but at a vastly larger scale. The mechanics of this pressure wave stem from basic physics of fluid dynamics. As the asteroid transfers its kinetic energy to Earth, much of this energy converts to heat, creating an expanding bubble of superheated gas. This rapid expansion displaces the surrounding air with such violence that air molecules cannot move out of the way quickly enough. Instead, they pile up at the leading edge of the expansion, creating a wall of compressed air that moves outward at supersonic speeds. This compressed air contains extraordinary pressure differentials, increasing almost instantaneously from normal atmospheric levels to potentially hundreds of times higher before dropping again as the wave passes. The resulting forces demolish nearly any structure and devastate living organisms. Mapping the destruction reveals concentric circles of devastation extending outward from impact. At 100 kilometers from ground zero, the pressure wave arrives approximately 5 minutes after impact, carrying overpressure exceeding 30 pounds per square inch, 6 times the threshold needed to demolish reinforced concrete. The pressure front follows an intensely bright flash and extreme heat. Buildings collapse completely, even the strongest structures crumble to rubble. For the people experiencing this moment, there would be barely time to process the initial flash before the devastating wall of pressure ends all awareness. At 500 kilometers, the pressure wave arrives approximately 25 minutes after impact, with overpressure of 5 to 7 pounds per square inch. This level remains sufficient to severely damage most conventional structures. Residential buildings collapse entirely, while some specialized reinforced structures might remain standing, but with severe damage. Windows shatter across this entire region, sending glass fragments flying at deadly speeds. Some people might have time to witness the approaching destruction on the horizon, perhaps even attempting to shelter or reach loved ones before the wave arrives. At 1,000 kilometers from ground zero, the pressure wave arrives approximately 50 minutes after impact, with overpressure of 2 to 3 pounds per square inch. While significantly weakened, this remains powerful enough to blow out windows, damage structural elements, and cause partial collapses of weaker structures. The destruction would resemble the aftermath of a major bombing campaign, with significant casualties but also many survivors requiring immediate medical attention that would be unavailable. The weakening of the shockwave follows an approximately inverse cube relationship with distance. Doubling the distance reduces overpressure by roughly a factor of 8. The 20 psi contour, where virtually all structures collapse and fatality rates approach 100%, would extend approximately 300 kilometers from impact. The 5 psi contour, causing significant building damage and many fatalities, would reach roughly 700 kilometers. This destruction radius dwarfs the largest volcanic eruptions in recorded history, with a destructive force thousands of times more powerful than the 1883 Krakatoa explosion. The effect on human bodies varies dramatically with distance. Within 200 kilometers, the pressure wave causes immediate death through pulmonary trauma, rupturing lungs as the pressure differential becomes too great for tissue to withstand, and traumatic brain injury as pressure creates damaging forces on brain tissue. Between 200 to 600 kilometers, many would survive the initial pressure wave, but suffer severe injuries including ruptured eardrums, pulmonary contusions, and internal hemorrhage compounded by environmental collapse and absence of medical treatment. Beyond 600 kilometers, direct deaths decrease, but injuries remain widespread from hearing damage, flying debris, and structural collapses. Different environments show varying resilience. Modern reinforced concrete structures with blast-resistant features might survive up to about 15 psi, extending their survival radius to perhaps 400 kilometers. Underground structures might remain intact even closer to impact, though occupants would likely perish from secondary effects like ground acceleration or thermal radiation. In contrast, typical wood frame homes would be destroyed by just 2 to 3 psi, flattened to distances of 1,000 kilometers or more. Bridges and highways would collapse across similar distances, while power lines would fail across even greater ranges, eliminating recovery infrastructure. Following the immediate pressure wave, hurricane force winds would compound the destruction. The passing blast wave creates a partial vacuum behind it, drawing air back toward the impact at extreme velocities exceeding 300 kilometers per hour. These winds would lift vehicles, topple damaged structures, and carry debris at lethal speeds, extending serious destruction hundreds of kilometers beyond the primary damage zone. The acoustic effects would propagate globally. Air-coupled seismic waves would circle the planet multiple times. Lower frequency infrasound would travel efficiently through the atmosphere, disrupting animal behavior thousands of kilometers away. Ground-coupled acoustic waves would travel through Earth's crust as seismic activity equivalent to a magnitude 10+ earthquake. This devastating overpressure zone would extend approximately 1,000 kilometers from impact, destroying most human-made structures across approximately 3 million square kilometers, roughly the size of India. Beyond this primary destruction zone, the pressure wave would continue globally, gradually transitioning from a destructive shockwave to a powerful acoustic phenomenon, still shattering windows and damaging structures thousands of kilometers away. The pressure variations would disrupt weather patterns worldwide. While this atmospheric shockwave spreads outward, an even more profound transformation occurs in the atmosphere above. The impact has ejected millions of tons of pulverized rock, vaporized material, and dust high into the atmosphere and beyond, beginning a journey that will transform Earth's atmospheric catastrophe. While the pressure wave spreads outward across Earth's surface, an even more profound transformation begins in the atmosphere above. The impact ejects an estimated 1 trillion tons of material into the atmosphere, a mixture of pulverized asteroid fragments and terrestrial crust. This mass of material includes pulverized rock, superheated vapor, and microscopic particles that begin their journey through Earth's atmospheric systems. The initial ejection creates a plume of debris that rises far beyond the troposphere, pushing material directly into the stratosphere and mesosphere. Within minutes, debris reaches altitudes exceeding 50 kilometers. The composition varies significantly based on the impact site's geology. Continental impacts inject silicates and crustal minerals. Oceanic impacts release water vapor with dissolved salts, and impacts on sulfur-rich sedimentary rocks release enormous quantities of sulfur compounds into the upper atmosphere. This atmospheric injection follows complex distribution patterns governed by physics. The debris cloud expands outward from the impact site in a roughly conical pattern. Heavier particles fall back to Earth almost immediately, while lighter particles remain suspended. The finest particles, measuring less than 10 microns in diameter, can remain airborne for months or years. The atmospheric effects are immediate and severe. Sulfur compounds transform into sulfuric acid aerosols by reacting with water vapor, forming a persistent haze. Carbon compounds combine with oxygen to form carbon dioxide and carbon monoxide. Simultaneously, microscopic dust particles spread through atmospheric circulation, creating a light-blocking blanket that encircles the globe. This toxic shroud acts like a suffocating veil, progressively dimming sunlight across the planet. The impact generates a thermal pulse, an intense heat wave radiating outward through the atmosphere. This heat transfers via radiation at light speed, conduction through gases, and convection as heated air rises. Air temperatures briefly spike by dozens or hundreds of degrees in regions near the impact. The superheated air expands rapidly, creating powerful updrafts that pull in surrounding air and generate strong surface winds, effectively forming a massive impact-centered superstorm. Chemical reactions in the atmosphere amplify the devastation. The extreme temperatures cause nitrogen and oxygen to combine, forming nitrogen oxides on a planetary scale. These compounds react with moisture to create nitric acid rain with pH levels potentially below 3. This acidic precipitation poisons freshwater ecosystems, kills vegetation, and corrodes exposed surfaces. Additionally, these same nitrogen oxides catalytically destroy stratospheric ozone, allowing harmful ultraviolet radiation to reach the surface, adding radiation stress to already compromised ecosystems. Within 24 hours, the debris plume spreads along prevailing wind patterns. Stratospheric particles travel at 100 to 200 kilometers per hour through upper-level winds, creating an expanding cloud of contaminants that begins in one hemisphere but spreads globally within approximately 1 week. This atmospheric transformation resembles a rapidly expanding toxic blanket, progressively wrapping around the planet. Temperature effects vary dramatically by region. Areas near the impact experience extreme heating from the thermal pulse, hot enough to ignite material spontaneously. This heating quickly gives way to cooling as the debris cloud blocks solar radiation. Within days, surface temperatures drop across increasingly large regions. Coastal areas experience somewhat moderated changes due to oceanic thermal inertia, while continental interiors show more extreme cooling. The most dramatic temperature drops occur in regions already experiencing winter conditions. The particle injections transforms global weather patterns. Temperature differentials create powerful pressure gradients driving unusual wind patterns. Normal atmospheric circulation, including jet streams, trade winds, and monsoon patterns, becomes severely disrupted. This disruption generates chaotic weather, including intense storms, unusual precipitation, and wind shifts. The thermal contrast between heated air masses and rapidly cooling regions generates massive storm systems. Regions thousands of kilometers from impact experience unprecedented meteorological phenomena. Precipitation patterns shift dramatically as particulates provide abundant condensation nuclei, initially triggering heavy rainfall. This quickly gives way to precipitation suppression as atmospheric cooling reduces moisture capacity, resulting in brief intense rainfall followed by extended drought. Earth's atmosphere becomes a toxic, turbulent system wholly different from its pre-impact state. The combination of stratospheric dust, sulfuric acid, nitrogen compounds, and water vapor creates an atmospheric environment incompatible with many life forms. Sunlight diminishes to twilight or darkness in heavily affected regions. The air becomes acrid with particulates and acidic compounds. Temperature patterns destabilize, creating wild swings between brief heating and prolonged cooling. Weather systems turn violent and unpredictable. For survivors on the ground, the experience transforms from the immediate catastrophe to an equally frightening new reality. The sky darkens to an unnatural twilight that deepens progressively. Breathing becomes difficult as fine particulates and acids infiltrate the air. The atmosphere, once life's protective shield, becomes its poison. This toxic blanket not only blocks vital sunlight, but actively delivers deadly compounds to Earth's surface through precipitation and direct contact. These atmospheric changes occur with remarkable speed, transforming Earth's entire atmospheric system within days, and create the foundation for the longer-term climate collapse that follows. The very air that once sustained life becomes a delivery system for compounds that attack biological processes at every level, from cellular damage via acid exposure to ecosystem collapse through temperature destabilization and diminished photosynthesis. Life forms evolved over millions of years to thrive in specific atmospheric conditions, now face an environment altered beyond recognition in mere days. The first hours for survivors. For those located beyond the initial blast radius, Survival would depend largely on geography. At distances of 1,500 to 2,000 kilometers from impact, the immediate shockwave would have weakened enough that structures might remain partially intact. Mountain ranges would provide crucial shielding, creating shadow zones where pressure wave effects diminish. Deep valley systems, particularly those oriented away from the impact, might offer protection from the direct blast. Underground structures like subway systems, mines, or specialized bunkers would provide the greatest immediate protection, though their long-term viability would depend on supplies and air filtration. The most fortunate survivors would be those positioned on the opposite side of the planet from impact, the antipodal point. Here, the shockwave would converge after traveling around the globe, creating localized destruction, but the immediate effects would be significantly reduced compared to regions closer to ground zero. Islands distant from continental landmasses might fare better initially, though they would subsequently face isolation and resource limitations. Picture a family in rural Montana taking shelter in an abandoned mine shaft as the sky transforms above them. For survivors like them, the first noticeable change would be the sudden transformation of the sky. Those with a direct line of sight to the impact would witness an unprecedented flash brighter than the sun, followed by a rapidly expanding fireball rising above the horizon. This initial flash would be visible hundreds or thousands of kilometers away, appearing as a second sun briefly illuminating the landscape with harsh, directional light. Within minutes, this brilliant illumination would give way to darkness unlike anything in human experience. The ejected debris cloud would begin blocking sunlight, creating a twilight that deepens progressively over hours. The sky would take on an unnatural coloration, first copper or bronze, then transitioning to deep red or purple as light wavelengths scattered through the thickening particulate layer. The psychological impact of this sudden darkness would be profound. Humans have evolved with the reliable cycle of day and night as a fundamental constant. The abrupt disruption of this pattern would trigger deep psychological distress. The darkness would obscure vision and reinforce the scale of the catastrophe. This darkness would immediately complicate all survival efforts. Navigation would become difficult as landmarks disappear. Search and rescue operations would be severely hampered. Simple tasks would require artificial light sources, which would soon fail as power systems collapse. Modern communication would disintegrate quickly. The asteroid impact would generate an electromagnetic pulse, destroying unshielded electronic devices across continent-sized regions. Physical infrastructure would collapse from the pressure wave. Within hours, global communication would fragment into isolated pockets, leaving many wondering if they were the only survivors. The air would become an immediate threat. Impact debris would begin falling back to Earth, creating a deadly rain of material. As finer particles filled the atmosphere, breathing this contaminated air would cause respiratory distress. The finest particles would penetrate deep into lung tissue, causing inflammation and potentially long-term damage. Some survival experts have long theorized that marine environments might offer unexpected refuge during such scenarios, submarines or deep-sea research. Stations could provide both protection and access to ocean resources, a strategy we'll explore further. Temperature extremes would create additional challenges. In regions affected by the thermal pulse, temperatures would briefly soar high enough to ignite materials. This initial heating would give way to rapid cooling as sunlight diminishes, potentially decreasing by 10 to 15 degrees Celsius within 24 hours in continental areas, creating an immediate hypothermia risk. Consider a group of office workers trapped in the basement of a partially collapsed high-rise, huddling together for warmth as temperatures plummet, using salvaged materials to create insulation. Secondary disasters would compound these challenges. For coastal regions, tsunami waves would begin arriving within hours, potentially reaching hundreds of meters in height near the impact. Critical infrastructure systems, electrical grids, water systems, transportation networks would fail in cascading sequences, quickly returning affected regions to pre-industrial conditions. Societal cohesion would face extreme pressure. Some communities would demonstrate remarkable cooperation, with individuals sacrificing for collective survival. Others would experience breakdown of social order as resource competition intensifies. Institutional response capacity will be overwhelmed, leaving most survivors to rely on immediate community resources. The search for necessities would become the central focus. Clean water would become immediately scarce as municipal systems fail and surface sources become contaminated. Food access would split along urban-rural lines, with urban populations quickly exhausting accessible supplies while agricultural regions might maintain access to local production. Medical challenges would overwhelm remaining healthcare capacity. Beyond direct injuries, survivors would face respiratory illnesses, waterborne diseases, and cold-related conditions. Medical supplies would quickly deplete with no resupply chain, forcing a return to basic first aid and improvised treatments. By the end of the first 24 hours, survivors would witness an astronomical phenomenon unlike anything in human history. The darkened sky would take on an eerie luminescence as particles in the upper atmosphere scatter the limited remaining light. Depending on the chemical composition of the debris cloud, the sky might appear deep red, purple, or even a sickly yellow-green. This darkness would not be uniform. The sky would show unsettling dynamics as debris concentration shift, creating moving patterns of lighter and darker regions. The familiar blue of Earth's sky would be entirely absent, replaced by alien coloration. As the first day ends, the focus would shift from the atmosphere to another critical Earth system undergoing catastrophic change. The oceans, covering 71% of our planet's surface, would now be absorbing and redistributing the asteroid's energy in ways that would transform survival prospects for all remaining life on Earth. Oceanic upheaval. The oceans would face their own catastrophic transformation following the asteroid impact. When a 10-kilometer asteroid strikes an ocean, the energy transfer creates physical dynamics utterly unlike any natural ocean process. Water behaves uniquely under the extreme forces of an asteroid impact, generating waves that defy comparison to typical tsunamis or storm surges. Asteroid tsunamis fundamentally differ from earthquake-generated ones. Instead of tectonic plates shifting the seafloor, the asteroid plunges through the water at hypersonic speed, transferring kinetic energy directly to the seafloor. This creates a massive cavity, a temporary hole extending to the ocean floor. This displacement forms a towering wall of water surrounding the impact point, with initial heights reaching kilometers near ground zero. As the cavity collapses, a massive central jet of water rises to stratospheric heights before crashing down, generating complex secondary wave patterns. These tsunamis propagate outward in all directions at approximately 800 kilometers per hour, matching a commercial jetliner's speed. In deep water, they might measure only meters in height while conserving enormous energy across ocean basins. When approaching shorelines, their wavelength decreases while height increases dramatically through shoaling, transforming into walls of water potentially hundreds of meters tall. Coastal impacts would vary dramatically based on topography. Gradually sloping continental shelves might see lower wave heights, but greater inland penetration, while steep offshore slopes could produce extreme concentrated wave heights. Funnel-shaped bays would amplify waves through constructive interference, potentially doubling or tripling tsunami heights at these focus points. For our 10-kilometer asteroid scenario, coastlines within 1,000 kilometers might face initial waves exceeding 100 meters, taller than a 30-story building. At 5,000 kilometers, from impact, waves might still reach 20 to 50 meters. Even coastlines on the opposite side of the globe could face devastating 5 to 15 meter tsunamis. A horrifying waiting period would unfold based on distance from impact. Nearby regions would have almost no warning, with waves arriving minutes after the atmospheric pressure wave. Areas 1,000 kilometers away would have 1 to 2 hours before tsunami arrival, while coastlines 5,000 kilometers distant might have 5 to 6 hours. However, with communication systems compromised, coordinated evacuation would be virtually impossible. The tsunami would arrive as multiple waves separated by minutes or tens of minutes. Often, the first indication would be an unusual rapid withdrawal of water from shorelines as the trough preceding the wave crest arrives, briefly exposing the seafloor before the towering wall of water crashes ashore. Inland penetration would exceed anything in human experience. Flat coastal plains might see inundation extending tens of kilometers inland. River valleys would channel tsunami energy far upstream, potentially carrying destruction hundreds of kilometers from the coast. Only hills taller than the local wave height, potentially exceeding 50 meters in many regions, would provide protection. Urban environments would offer minimal resistance. The tsunami would move not as breaking surf, but as a rapidly rising flood with enormous energy, carrying a grinding slurry of concrete, metal, and debris that magnifies its destructive power. Few structures could withstand both the hydrostatic pressure and debris impacts. Beyond mechanical destruction, the impact would trigger profound changes to ocean chemistry. Massive quantities of particulate matter would settle onto ocean surfaces worldwide, including asteroid fragments containing rare metals, pulverized terrestrial rock, and compounds created during impact. This material would alter ocean chemistry as it dissolves in seawater. Though iron and other nutrients might temporarily stimulate phytoplankton growth in certain regions, negative changes would predominate. The dissolution of impact compounds would lower ocean pH, threatening marine organisms with calcium carbonate structures like corals, mollusks, and plankton species. Temperature fluctuations would compound these stresses. Regions near impact would experience extreme heating, with water temperatures rising dozens of degrees, immediately lethal to most marine life. As atmospheric debris blocks sunlight, surface temperatures would subsequently plummet, creating thermal stress in the opposite direction that exceeds most species' adaptive capacity. The asteroid would also disrupt ocean circulation patterns critical for climate regulation. Ocean currents that redistribute heat from equatorial regions toward the poles would be temporarily disrupted through direct mechanical force, altered temperature gradients, and potential freshwater input from melted ice. These circulation changes would profoundly affect global climate regulation. Major current systems like the Gulf Stream could weaken or shift. Upwelling zones critical for marine productivity might cease functioning. Temperature differentials between equatorial and polar regions could temporarily increase, further destabilizing weather patterns. Marine ecosystems would face catastrophic pressure from these combined stresses. The immediate pressure wave would kill marine life directly throughout an ocean basin. Tsunamis would destroy critical coastal habitats, including spawning areas, mangroves, and coral reefs. Chemical changes would threaten organisms at all trophic levels, while temperature fluctuations would exceed survival thresholds for many species. Primary producer collapse would trigger cascading failures through marine food webs. The oceanic systems covering more than 2/3 of our planet would transform from life-supporting to life-threatening. The stable chemical and physical properties of seawater that have persisted for millions of years would rapidly shift beyond the tolerance of most marine organisms. Ocean currents that have regulated Earth's climate throughout human existence would reorganize, setting in motion climate changes that would persist long after the immediate catastrophe. While the atmosphere fills with debris and the oceans transform through chemical and physical changes, the solid Earth itself experiences its own profound response to the asteroid strike. The impact energy penetrating through the crust triggers geological processes that further reshape the planet's surface. The Firestorm Earth. As debris darkens the sky and oceans surge with unprecedented tsunamis, another destructive force emerges: fire. The asteroid impact creates ideal conditions for widespread combustion through multiple distinct mechanisms. The initial thermal radiation from the impact site, essentially an enormous flash of heat traveling at light speed, ignites flammable materials hundreds of kilometers away. Dry, vegetation, exposed fuels, and human-made structures burst into flames simultaneously across vast regions. The impact triggers several devastating ignition waves. First comes the thermal flash, and minutes later, ejected material returns to Earth as billions of superheated particles functioning like tiny meteorites, creating countless ignition points across continents. The atmosphere itself becomes electrically unstable, generating unprecedented lightning storms that ignite regions already primed for burning. Peaceful forests that once whispered in gentle breezes now crackle with advancing flame fronts. The acrid smell of burning wood hanging heavy in air that grows increasingly thin. The global spread of these wildfires follows patterns determined by fuel availability and weather conditions, though these patterns rapidly destabilize as impact effects unfold. Boreal forests across northern latitudes, Canada, Russia, and Scandinavia present ideal conditions for massive fire complexes. Their coniferous vegetation, rich with flammable resins, typically grows in dense, continuous stands that enable rapid fire transmission. The familiar scent of pine transforms into choking smoke as centuries-old trees become towering torches. Temperate forests burn somewhat less intensely than coniferous regions, but still support massive fire complexes. Tropical rainforests initially resist ignition due to their high moisture content, but as impact-induced drought intensifies, even these normally fire-resistant ecosystems become susceptible to burning. Grassland and savanna regions support extremely rapid fire spread. Flames can advance at dozens of kilometers per hour, but produce less intense heat and typically consume available fuel quickly. What makes this scenario catastrophic is the simultaneous occurrence of multiple ignition sources. Typical wildfire events begin at discrete points, with firefighting resources concentrating on controlling expanding fire fronts. The post-impact environment creates ignition at millions of points simultaneously, forming fire fronts that rapidly merge into unprecedented conflagrations. The gentle rustling of leaves gives way to the roar of approaching flame walls, punctuated by the explosive cracking of trees as their moisture flash converts to steam. As these massive fire complexes develop, they generate their own weather systems. The concentrated heat creates powerful updrafts, forming pyrocumulonimbus clouds, fire-generated thunderstorms extending into the upper troposphere. These systems accelerate combustion by creating strong, erratic surface winds that push flames in unpredictable directions and speeds. The largest complexes transform into firestorms, a phenomenon where concentrated heat generates a central updraft so powerful that surface winds rush toward the fire from all directions. During World War II, the Dresden firestorm generated 240 kilometers per hour winds flowing toward the fire center. Post-impact firestorms potentially exceed these intensities and cover thousands of square kilometers. The deafening roar of these systems drowns all other sounds, creating an apocalyptic backdrop to the visual horror of landscapes transformed into furnaces. The atmospheric chemistry changes dramatically as continental scale fires consume available oxygen. While global oxygen levels wouldn't decrease substantially, localized depletion creates areas where concentrations temporarily drop below the 19.5% threshold considered minimum for human survival. This combustion converts atmospheric oxygen primarily to carbon dioxide, with significant carbon monoxide production in areas of incomplete combustion. The fires also produce enormous quantities of particulates, soot, ash, and various aerosols that further darken the already debris-filled atmosphere. These fire-generated particulates compound the light-blocking effects from impact debris, accelerating cooling and intensifying the developing impact winter. Smoke particles contain high carbon content and organic compounds, including toxic substances like formaldehyde, benzene, and acrolein, creating severe respiratory hazards when combined with the already degraded air quality from impact dust. Critically, these fires destroy remaining vegetation across vast regions. The combination of impact effects and fire eliminates not only current plant growth, but also seed banks in surface soil layers. This destruction has cascading effects through ecosystems, eliminating food sources for herbivores and subsequently for predator species. For human survivors, the fires destroy both standing crops and agricultural infrastructure, eliminating food precisely when most needed. Fire duration depends on fuel availability, weather conditions, and regional fire behavior. In areas with dense forest cover and abundant fuel, fires continue burning for weeks to months until either all available fuel is consumed or significant precipitation finally extinguishes them. The impact-induced climate. Disruption reduces normal rainfall patterns, extending fire duration beyond typical wildfire events. These post-impact fires transform approximately 30 to 50% of Earth's land surface through direct burning, with additional areas affected by smoke. The majority of Earth's forests and grasslands are consumed, converting most terrestrial biomass to atmospheric carbon dioxide and particulate matter, one of the most rapid and extensive changes to Earth's surface environment in geological history. When the fires finally extinguish, they leave behind a fundamentally altered landscape. Formerly forested regions become barren ash fields. Soil structure changes as organic components burn away, leaving mineral soils susceptible to erosion once precipitation returns. The combustion products remain in the atmosphere, continuing to influence climate long after the fires themselves end. With Earth's surface transformed by impact, tsunamis, atmospheric destruction, and now fire, we must ask whether humanity possesses the knowledge and could we prevent it? After witnessing the catastrophic aftermath of an asteroid impact, a question naturally arises. Could we actually prevent such a disaster? The answer depends on two critical factors: how much warning time we have and how effectively we can deploy our limited planetary defense technologies. Our current detection capabilities form the foundation of any prevention strategy. NASA's Jet Propulsion Laboratory operates the Asteroid Watch program, which tracks near-Earth objects that might pose a threat. As of late 2022, this program had successfully identified about 90% of near-Earth asteroids larger than half a mile wide. The good news is that none of these known large asteroids shows a significant chance of hitting Earth in the foreseeable future. However, detection represents only half the equation. Can we effectively change an asteroid's course once we find it? This is where significant technological gaps exist. With years or decades of warning, several promising deflection methods become viable. With only months of warning, our options narrow dramatically. And with just days or hours, as in our hypothetical scenario, prevention becomes nearly impossible with current technology. The most thoroughly tested deflection method is the kinetic impactor approach. This technique involves deliberately crashing a spacecraft into an asteroid to alter its trajectory through momentum transfer. In 2022, NASA's Double Asteroid Redirection Test DART mission successfully demonstrated this concept by intentionally colliding with Dimorphos, a small asteroid moonlet orbiting the larger asteroid Didymos. The impact changed Dimorphos' orbital period by about 32 minutes, proving that humans can intentionally alter the motion of a celestial object. While the DART mission marked a critical milestone in planetary defense, our hypothetical 10-kilometer asteroid contains billions of times more mass than the 160-meter Dimorphos. Could we scale up this approach to handle such massive objects? We would need either much larger impactors or much longer lead times to gradually shift its trajectory over years or decades. Another promising approach is the gravity tractor concept. This method uses the mutual gravitational attraction between a spacecraft and an asteroid to slowly pull the asteroid into a different orbit. The spacecraft maintains a constant distance using low-thrust engines, providing precise control and avoiding fragmentation risks. However, even a massive gravity tractor spacecraft would need decades to produce a meaningful orbital change for a 10-kilometer asteroid. When facing larger asteroids or shorter warning times, many scientists consider the nuclear option. This approach involves detonating a nuclear explosive device near an asteroid, offering much higher energy density than conventional methods. But how reliable would this be against a cosmic threat? The effectiveness depends heavily on the asteroid's composition and structure. A loosely bound rubble pile asteroid might fragment rather than deflect, potentially creating multiple impact threats. Additionally, international treaties prohibit nuclear weapons in space, complicating both development and deployment. Can the world unite against an asteroid threat? International coordination represents another significant barrier to effective planetary defense. The United Nations has established the International Asteroid Warning Network, IAWN, and the Space Missions Planning Advisory Group, SMPAG, to coordinate global responses. IAWN coordinates asteroid tracking efforts worldwide, while SMPAG focuses on developing collaborative research and mitigation plans. Events like the Planetary Defense Conference bring together scientists, engineers, and emergency managers to improve coordination. However, significant gaps remain in decision-making authority and funding responsibilities. If an incoming asteroid threatened a specific region, who would authorize a deflection mission? Who would fund it? These questions remain largely unanswered at the international level. Funding limitations further constrain our defensive capabilities. Despite the existential risk posed by large asteroid impacts, NASA's entire planetary defense budget represents less than 0.1% of its overall funding. Are we investing enough to ensure our survival? This limited investment slows the development of detection systems and deflection technologies that could prove essential. The situation is gradually improving. NASA's NEO Surveyor mission, scheduled for launch no earlier than September 2027, will enhance asteroid detection capabilities by leveraging infrared technology. The mission aims to discover 90% of near-Earth asteroids 140 meters or larger within a decade of launch, significantly expanding our early warning capacity. Other assets like the James Webb Space Telescope are being repurposed to support planetary defense. In March 2025, it observed asteroid 2024 YR4, which had a small chance of impacting Earth. These observations helped refine assessments of the asteroid's size and trajectory, demonstrating how even general-purpose scientific instruments can contribute to planetary defense. What technologies could prevent an extinction-level asteroid impact like the one that ended the dinosaurs? We have several approaches: kinetic impactors, gravity tractors, and nuclear options. But they all share a critical limitation. They require years of warning time to be effective, especially against larger asteroids. This limitation underscores the importance of early detection. With sufficient warning, ideally decades, even our current technologies could potentially deflect a 10-kilometer asteroid. With years of warning, we might successfully divert smaller but still dangerous asteroids. But with only 24 hours of warning, as in our hypothetical scenario, no current technology could prevent impact. The sobering reality is that planetary defense represents a race against time. Every additional day of warning exponentially increases our chances of successful deflection. This makes investment in better detection systems perhaps the most critical component of planetary defense. We cannot deflect what we cannot see coming. As we contemplate these technological challenges, Earth's previous encounter with a massive asteroid provides crucial lessons on why prevention efforts remain essential for humanity's long-term survival. Lessons from the dinosaurs. 66 million years ago, our planet experienced an impact scenario remarkably similar to the one we've been exploring. The Chicxulub asteroid, nearly identical in size to our hypothetical planet killer at approximately 10 kilometers in diameter, struck what is now Mexico's Yucatan Peninsula. This wasn't merely a historical footnote, it marked the most recent mass extinction event in Earth's history and permanently altered life's evolutionary trajectory. The impact crater itself tells a compelling story. Centered near the town of Chicxulub on the Yucatan coast, the crater measures about 180 kilometers in diameter, roughly the distance from New York City to Philadelphia. Its massive size reflects the extraordinary energy of the impact. Scientists have determined the asteroid struck at an angle of about 60 degrees, coming from the southeast, a trajectory that maximized the environmental damage by ejecting more material into the atmosphere. The timing of this impact precisely coincides with the Cretaceous-Paleogene boundary, a thin layer of sediment found worldwide that marks the dividing line between geological periods. Before this boundary, dinosaur fossils are abundant. Immediately after, they disappear entirely from the fossil record. This perfect temporal alignment provided the first major clue connecting the impact to the mass extinction. The evidence supporting the impact hypothesis extends beyond this correlation. The worldwide layer of iridium found precisely at this boundary serves as compelling evidence. Iridium is extremely rare in Earth's crust, but common in asteroids. The layer contains iridium concentrations up to 300 times above normal background levels. This iridium anomaly was first discovered by physicist Luis Alvarez and his geologist son Walter Alvarez in 1980, providing solid evidence connecting an asteroid impact to the dinosaurs' extinction. Additional geological markers support this conclusion. The boundary layer contains shocked quartz that forms only under extreme impact conditions, and tektites, glass spherules from rock melted during impact. These materials appear precisely at the extinction boundary, further confirming the violent event that occurred. The Chicxulub impact, in our hypothetical scenario, would produce nearly identical initial effects. Both involve asteroids of similar size striking at similar velocities. The Chicxulub asteroid released energy equivalent to roughly 100 trillion tons of TNT, approximately 10 million times more powerful than the largest nuclear weapon ever detonated. The fossil record reveals the devastating consequences. Approximately 75% of all species on Earth disappeared within a geologically brief period following the impact. The extinction affected dinosaurs, marine groups like ammonites and mosasaurs, numerous plant species, flying pterosaurs, and countless smaller organisms across all environments. Evidence suggests that many deaths occur rapidly. In North Dakota, a remarkable fossil site called Tanis preserves fish with impact debris embedded in their gills, suggesting they died within hours of the impact as ejecta rained down. Plant fossils show a sudden transition from diverse Cretaceous species to a post-impact landscape dominated by ferns, the first plants to recolonize after catastrophic disturbances. Not everything died, however. The survivors reveal important patterns about resilience to asteroid-induced extinction. Small, burrowing animals fared better than larger. Surface-dwelling species. Freshwater ecosystems showed higher survival rates than marine environments. Among the most successful survivors were early mammals, our distant ancestors. These small, primarily nocturnal creatures already possessed adaptations for surviving in darkness and maintaining constant body temperature during environmental fluctuations. Without the asteroid impact, mammals might have remained small, secondary players in dinosaur-dominated ecosystems. Other notable survivors included crocodilians, turtles, and birds, the direct descendants of dinosaurs. Birds represent the only dinosaur lineage that survived, likely owing to their small size, flight capability, and efficient respiratory systems. The recovery timeline following the Chicxulub impact reveals how long Earth takes to heal from such catastrophic wounds. Marine plankton populations began recovering within a few thousand years. Terrestrial plant communities took approximately 10,000 years to regain significant diversity. Full forest recovery required 100,000 to 300,000 years. For animals, especially larger vertebrates, restoring ecological complexity took millions of years. Full ecosystem recovery, measured by the restoration of complex food webs, required approximately 10 million years. This extended time frame emphasizes that while life proves remarkably resilient, recovering from extinction-level events occurs on timescales essentially meaningless to human civilization. The evolutionary consequences of the Chicxulub impact were profound. The asteroid essentially reset Earth's evolutionary trajectory. Had it missed Earth, non-avian dinosaurs would likely have continued their 165 million year dominance. Mammals might never have evolved beyond small, nocturnal insectivores. Primates and ultimately humans might never have evolved at all. This impact represents a significant random event in Earth's biological history, a cosmic accident that redirected evolution toward mammalian dominance, eventually making human existence possible. Our entire civilization exists because an asteroid happened to intersect Earth's orbit at a particular moment 66 million years ago. With this understanding of Earth's impact history, what does our future hold? We exist in a solar system still filled with potential impactors. The same physics that delivered the Chicxulub asteroid remains operational today. Yet, unlike the dinosaurs, we possess something unprecedented: the capacity to detect these objects and potentially prevent impact. Today's planetary defense efforts directly build on the lessons learned from studying the Chicxulub event. By understanding the precise mechanics of past impacts, scientists can better model potential future scenarios. Our tracking systems, deflection technologies, and international cooperation frameworks represent humanity's first attempt to break the cycle of random cosmic catastrophes that have repeatedly shaped Earth's history. This fundamental difference, awareness and technological capability, separates us from all previous species that faced cosmic threats, offering a unique possibility, the prevention of our own extinction. Throughout this exploration of an asteroid impact scenario, we've seen both our vulnerability and our unique capability to prevent extinction. The physical forces unleashed by a 10-kilometer asteroid would transform Earth's systems beyond recognition, yet we possess something the dinosaurs lacked: awareness and technology. Our detection systems and deflection capabilities offer genuine protection against cosmic threats. The DART mission proved we can alter an asteroid's path, a watershed achievement in Earth's history. We stand as Earth's first line of defense in the cosmic storm. As NASA Planetary Defense Officer Lindley Johnson noted, asteroid impacts represent the only natural disaster we now